Hi all and welcome to the first of the LINX Presents series. My name is Holly and I'm part of the LINX marketing team. As the current situation has seen all of our in-person events cancelled or postponed, LINX are trying wherever possible to move all our events online, including our member meetings and more training webinars like this. So please keep an eye out on our virtual events page to find more information and get access to the relevant registration pages. If you'd like to see us doing more of these training sessions and have any ideas on topics, give us a quick email at marketing@linx.net and we'll get this looked into for you. Now, enough of me, I'll pass you on to our trainer Brian Rushby from System and Network Training for your training session on Wireshark's tips and tricks. Enjoy.
Thank you very much, Holly, and thanks everybody that's took the time to attend. A little bit about SNT. This is not a sales pitch by any stretch, but that's just a little bit about what we do. Provide technical instructor-led training. Obviously, with the current situation as it is, all of our training has moved online. We're the provider for all the LINX 1, 2, and 3 courses, so the very start, sort of the basic network engineering stuff, through to the more complex topics around BGP, MPLS, etc. We also run a 3- and 5-day courses, Wireshark courses that are geared towards achieving the WCNA qualification. And there's some contact details below. So a little bit about Wireshark before we start. A little link on there. We're not going to play that now. It's deemed as one of the most important open source software application that's out there today. Great tool invented by this guy, Gerald Coombs. Originally called Ethereal, now Wireshark. There's literally 90 man years worth of development that's gone into this. It's a real labour of love for those that are concerned. So there's a lot of stuff that's gone into it. And that little Vimeo link shows a little graph of how it's all come together over the years. So what we're going to do today then, well, we're going to look at some tips and tricks. The thing that you must understand with Wireshark is that there's no point just being able to navigate the application. You must be able to understand, some details about what those packets are, what those protocols that are running, that are managing our networks. We're going to do a little bit on plumbing, so how we're going to actually get that information, where we're going to need to tap into the network, and what different methods are available to us and which are the best ones for certain situations. And we'll wrap it up with looking at how we can work a bit more efficiently with Wireshark. So looking at different profiles that we can use. So maybe one for wireless networking or one for troubleshooting something with HTTP, for example. So that's a little bit about network analysis, and that's really what Wireshark as a tool is designed for. It's the process of listening to and then analyzing that network traffic. It enables us to identify performance problems, finding potential security breaches, and analyzing behavior of applications, and obviously our networks. To sum it up, it's a process used by IT engineers in order to find and fix performance and security issues. And these are just some of the common troubleshooting tasks that you're going to be doing when we're using Wireshark. We're locating misconfigured or faulty network devices. When I say misconfigured, what we've got to understand now is our network devices are so high tech and have the ability to do this fine tuning for us. If there is something that's been done in a certain direction, one of the endpoints may not actually see or understand what's going on. That can potentially lead to a lot of problems. It enables us to measure potentially high delays along a path, and again find out why that's being delayed. Is there something in the path that's doing some deep packet inspection, for example, that's causing some issues? And we can locate where packet loss is occurring. So let's have a look at Wireshark itself. Let's go into it. Okay, so the first thing that you'll notice, if we just open up the screen, we can't really do much from here. We don't want to do too much from here. But we can see here we've got our interfaces that we can use, and these are known as spark lines, and we can see that there's traffic on here. And we could double click one of these to open up a capture. So if I just double click on Ethernet there, and I can see straight away that I've got packets arriving, and I'm capturing no problems. So I'm just going to stop that from scrolling because it's a bit distracting. I'm going to briefly just talk over this screen. So the first pane that we've got here, and it's this is the default profile that loads up automatically from Wireshark. So there's not done anything to this at the moment. In fact, I tell a lie because that wouldn't be in here. Been playing around. Okay, so we've got that information there. This is the packet list pane. So each one of these is an individual packet that's come in. We've got the packet details pane. So this is where it's going to break it down. Wireshark's applied the dissectors. We'll have a look at a little bit about that in a little while. But here's where we can see some a granular look at those frames. And then we've got the packet bytes field at the bottom. So if I just go across the top, so we can see we're actually capturing packets at the moment. So I can stop that capture there by hitting the red button. I can see that capture's going on at the moment. If I look at the bottom, I can see these packets that are being captured at the bottom. I could restart that capture, and if I stop it, I can then look at some different, start a new capture. So maybe capturing from a different interface, or maybe apply a capture filter. And we'll discuss those in a little more depth later on. If I want to go to the bottom of the packet, I go to the last packet here. I can go back up to the first packet. I can go to a particular packet if there's a specified one I want to look at, or I can just navigate back and forth. We can also use the arrows on our keyboards, for example. Obviously, you can't really see me doing that, so I won't use those. This button at the bottom here, should I say, this is going to scroll automatically to the last packet. So this is just going to keep ticking along. So we can drop this one off. We can also enable or take off the coloring rules that are applied. So for some people, they don't like to have the coloring rules on because when you've got a lot of different traffic coming in, lots of different colors, it can be a little bit distracting if we're trying to look for a certain thing. Some people might just drop it off initially. At the moment, you can see the text is quite small, so I can make this a little bit bigger. I could then auto adjust my columns to make that fit, or obviously reduce it with the shrink button, or I can just return it to the normal size. Okay, so that's just some of the initial things that you can look at. So as I said before, what we really want to be doing is having a bit of a better feel of Wireshark when we open it up. And this is, as I said, the default way that it will appear to you. So if I right click on the profile button in the bottom right hand corner here, I can click for a new profile. It'll be based on the default one to start off with. So I'm just going to put Wireshark webinar in here, bit of name. Okay, and we can see that profile's automatically gone onto it there. So any changes that I make now will be saved. Okay, so for example, I can go into my preferences and I can just alter the layout. So just as a very easy thing to do, I prefer to have it looking like this. So I've got my packet list field here, packet details, and then my packet bytes across. And I can adjust these just on the fly as and when I need. Again, I'm just going to stop that one from scrolling there. Okay, so that's a very brief introduction to the Wireshark screen. We'll be coming back to here, obviously, throughout the presentation. So let's just have a look at how Wireshark actually works first. Okay, so really there's two ways that we're going to be viewing capture files in Wireshark. We're either going to be doing a live capture, or we're going to be being sent a packet capture file that we're going to load up into Wireshark. So the first one we can see on the left-hand side here, we've got two drivers that are used in particular to capture traffic. So we've got WinPCAP for Windows, makes sense, being Windows Win. And then we've got libpcap for Linux and Mac. At this point here, we can apply some capture filters. So we can, if we're looking for a certain type of traffic, say we're only looking at VoIP, we might just apply some particular filters to do that, so that we're not overloading a span port, for example. The only thing to remember with, or should I say the main thing to remember with applying any capture filters is that once those are applied, you will not see you can't get those packets back. So if there is some packets that may have been interesting to what you was looking at, that they're now gone. All right. So if we do, the kind of suggested thing is not to really use capture filters too much unless they're needed. We can use display filters as much as we like, and that's not going to be a problem. So that's going to be loaded into dump cap, and then that's going to be fed into the core engine. Now the core engine is the heart of Wireshark. Right? This is where the dissectors can be applied. This is where all the cool stuff takes place. And then it can be fed into either the Wireshark GUI, as we're going to be looking at today, or it could be, we've got the CLI version T-Shark, which is used more for automation. We're not going to be covering that today. So if we're not doing a live capture, we've also got we can use the wiretap library. So this supports pretty much all known different capture file types. So whether we're doing a TCP dump or anything at all, we can load that into the Wireshark core engine, and we can get a read of those packets in Wireshark itself. Okay, so what I'm going to do is I'm just going to go back to Wireshark, and I'm going to load up a capture file. So I can see here I've got my open capture file, and let's go to my desktop, and I think thought this was already on. That's fine. There we are. Sure. Let's just pick one. Doesn't really matter. I can continue that without saving. I don't need to save any of those packets. And I can see I've loaded up a packet capture into Wireshark, and I can do I can analyze that. So that could have been maybe sent to me by a customer that's been having some problems, and I can then analyze that from there. Okay, so that's the loading up a capture filter. Loading up a capture file into Wireshark. We've had a little look at about how it works. And before we go too much further, let's do a little recap and just a little discussion really about the OSI and internet models as it's known now. So I'm sure most of, if not all of you, are familiar with the OSI model. And it's obviously the common language that we all speak as either a network engineer or whether you're on the application side. So as a network guy, I'm definitely responsible really for layers 1 to 3. So the physical layer, data link layer, and the network layer. Okay, this is definitely my job as a network guy. And we could almost certainly say as well that the top 3 layers, the application, presentation, and session, are really the responsibility of the application guys. Obviously, there's exceptions to everything, but what tends to get missed or at least discussed is whose responsibility is it for layer 4? So really, it's that age-old answer of it depends on the situation, really. So we know that a TCP/IP stack is something that's installed on a client or it's installed on a server. It's not necessarily the network itself. It's not that I can control. However, as I mentioned briefly earlier, with the devices that we've got now, the things that they do, they can obviously alter fields in that. Now, obviously, the obvious one that everyone will know is with network address translation. So if we're doing NAT and with overload, that NAT device is going to be going in there and it's going to be modifying the TCP ports, the source port. Okay, so in that case, then that network device, that device that's running on our network, would be the responsibility of the network guy. Okay, so hopefully that's clear on those responsibilities. So we're going to let's have a look at the Ethernet frame sort of breakdown. A lot of people will say that the preamble and the start frame delimiter, so each one of these, I've put the numbers next to them, is in bytes. So we've got the 7-byte preamble followed by the 1-byte start frame delimiter. So that preamble is basically telling the device, here's a frame on its way, here's where it starts, and the next field is going to be that destination MAC address, 6 bytes. Now, people say, well, we don't see that, so it doesn't matter. Well, it does matter. It's on the wire. It's bytes of data. It's something that we need to take into account with, you know, the utilization that's going on there. Just because we don't necessarily see it, it's definitely still there. We've got the destination MAC address and source MAC address. We've got that type, which is going to be 2 bytes, which is not on there. With here, this could be 46 to 1500. If we've got a VLAN tag, that's going to be put in there. And then at the back, which is just nipping into this next little bit, is going to be the frame check sequence as well, which is going to be 4 bytes in length. Now, obviously, this is, we're going to look at offloading. So some of the checksum offloading a little bit later on. But really we'll see that in Wireshark, when we're capturing on the client side at least, we're probably going to want to leave this disabled, which it is as default. We'll cover more on that shortly. So let's have a look at how that Ethernet frame looks in Wireshark. So just a point to note on this, and I'll just make this a little bit bigger. Okay, so when we move down to the packet details pane in Wireshark, the first thing that we see is this frame 1. So whichever frame that I select, it will tell me which frame it is. Frame, packet, sort of interchangeable terminology there on this part anyway. That's not saying that's the Ethernet header. So the Ethernet header is here. So when I click on those details here, I can see that Wireshark has actually done some work for me already. So where I've got that destination and source MAC address, it's actually resolved the manufacturer's OUI automatically for me. And now there's a file in Wireshark that you could go into and you can add ones to if you needed to do that, or you know you wanted to make a change, you can do that. But that's going to automatically resolve those for us. Yeah, and that's just some, if I click the little drop down, I'll get some more information on that as well. Okay, so we can see those basic header fields in the in Wireshark. What we're not going to see is the frame check sequence, because that's going to be calculated and done on the NIC itself. So what I'm going to do from here is just do a little bit of a filter on something. So we just pick anything. So if for example I wanted to just use this field here as a display filter, I can just pick that up and drop that into the display filter box. So the point to note on this is that we don't need to necessarily memorize tons and tons of display filters. So there's things that we can do in Wireshark where we can just pick something up, drop it in, or for example, we could say I want to apply this field as a filter. I want to apply what's here, what's selected. Okay, so we can make those changes there. So nice and easy, nice and straightforward. So that's the Ethernet header in Wireshark. So let's have a look. If we go back, we're going to look at the IP header. And then again, we'll have a look in Wireshark and do a little bit more on that. Okay, so the first field that we've got in the IP header is we've got the version. So it stands to reason that this is going to be 4 because it's IP version 4. We've got the header length. Obviously, we need to know that header length because obviously if there's options involved, you know, we need to know where that data within the packet starts. We've got the diffserv field, so basically quality of service. There's lots of different codes around that. Actually, these two here, the last two is for ECN. Okay, we'll see that when we get into Wireshark anyway. We've got the total length of the packet. We've got the identifier here. Now, some confusion, you can get confused with this, should I say, is that this identification field is the identity of that packet. So it's a number of that packet. And that's really useful to know. So if we're doing a capture between a client side and a server side, for example, we can look for the particular ID of that packet so we can match those up. And that can be a useful troubleshooting tool. What it is not is it doesn't describe what's inside the packet. So that's within the protocol field, and we'll come to that. So obviously this identification is crucial. If there is fragmentation on the network, then we need to be able to, or the receiver needs to be able to reassemble those packets. Okay, so we've got our flags here. So this is going to be telling us whether we can fragment. So obviously both the host may say, I don't want to fragment any of the bits, and we'll set that bit to say, don't fragment this packet. And if that's the case, and we hit a network device that doesn't support a certain MTU size that we're sending, it's going to drop the packet and should send us an ICMP message back to say, you know, we've dropped that packet. But that's not actually going to kick off any other action. If there is fragmentation that's taken place, then we've got that offset value so that the receiver knows which order the fragments need to be put back into. The next field we've got is the time to live. So the time to live is a number that's going to be decremented by each router on the path to its destination. So we can use this for things like traceroute, where it is set at 1 to the start, so it gets to that router, does that 3 times, comes back, etc., and does that, keeps increasing the time to live each time. As I mentioned, the protocol field, this is what's going to be describing what's actually contained within the packet. So if it's TCP, for example, then that's going to be described as TCP. We've got the header checksum. So I mentioned checksums briefly with the Ethernet trailer, a little bit different within the IP header. So what used to happen is obviously this calculation would be done. So some maths applied and a number put in that box. When it's passed up on the receiver, we check that checksum. And if it matched, great, no problem, we can move on. And if it's not, then obviously we've got problems. What we see now more commonly is that that work is going to be offloaded to the NIC card. So in Wireshark, when Wireshark sees a copy of the IP packet going out, it will just see it as 0, particularly on the client side anyway, on the sender side. But we'll have a look at that when we get to it. Okay, we've got source IP address and destination IP address. I'm sure you're both, I think there's a few more of you under than 2. It's 32 bits in length, both of those fields. We've got some options and then any padding that's needed. So options tend not to be used too much in the IP header. It could be an alert or something to do with the route or other details in there that can be used for sort of erroneous, not good reasons, should I say. And then obviously we've got the data packet itself. So let's have a look into an IP packet in Wireshark. What I'm going to do is I'm going to actually just take this one out. And let's capture some packets. Some coming in there. Okay. So I'll go into the, I can just pick any one. Most of these are using IP, and I can see that there because the IP addresses are in there for the source and destination. So that's a little look of what we're going to see in Wireshark. So we can see the high level information, basically telling us what the source and destination address is. We can see that version, and we can see the header length. Okay, so that's obviously in binary telling us it's 5, meaning 20 bytes. We've got that differentiated services field, and we can see that the ECN is there as well, the explicit congestion notification. So we can see here that my device here is saying I'm not capable of doing that. So because that's set at 00, that means that it's not capable of carrying out this this function. If it's set to 0 or 1 and 0, then it means it is capable, and that can help us out a bit further down the line. Okay, we've got that total length, and we've got the identification that I mentioned of the packet itself. So again, this is really useful if we're doing capture on both ends. Okay, we can see those flags. None of them have been set. We've got the fragment offset, again, not relevant. The time to live, common number we're seeing there is 128. We can see that the protocol field is 17, which means UDP. If I click on that, we can actually see that in the packet bytes pane as well. We've got the header checksum, and we can see here that the validation's been disabled. So what Wireshark has seen is that it's 000. Now, if I go to my preferences and go to protocols, now I can see here in the IP version 4, by default, Wireshark is going to turn off the validate IP checksum if possible. Now, if I turn that on and just let it catch up, okay, we can see that it's come up and it's telling us that this is incorrect. And the reason why it's incorrect, as I mentioned, is because by the time when Wireshark sees it, because that header checksum has been offloaded to the NIC card, it's not going to see it. Now, on the wire itself, that checksum is going to be fine. It's going to go on its way. It's not going to be a problem. Okay, I'll leave that off on for the time being. We can see our source and destination, and then we're moving into what's actually contained within the packet itself. So, for example, if we wanted to create some display filters based on this information that's here, I could, for example, say I want to look at all the packets that are going to this destination here. I can apply this one as a filter, so apply the selected, and there we go. And I can see there that there's, when it comes up, sorry, the thing might be in the way. I don't know if you can see that, but the packets that are there, and then the packets that are displayed. So everything that matches, so equals, everything that matches that IP address as the destination will be coming in there. We won't see anything else. Take that off. Again, when it's got a chance to catch up. And we can see the other stuff coming back in. Okay, so another thing that we can do is, for example, say if we wanted to, so I'm just going to drop this one in there. Okay, so I just need to move my face out of the way. We've got our IP time to live there as 128. So I can see everything that's going to be matching that now once Wireshark has rescanned it. What I can do, and this is quite a basic filter, probably wouldn't do it, but what I can do is I can create a button. So I can add a button that will automatically do this one. So I could give it a label and just say time to live 128, for example. Press OK. I can now take that one off. And if I wanted to reapply that, once that's calculated, I can just click that button. And we can see that the button works. Now, obviously, we're not going to do that for very basic, straightforward filters, but just know that feature's there and it is useful to us. Okay, so that's our IP packet. So let me jump back again. Now, this is my favorite protocol, TCP, and it really is. It's a great protocol and it's improving all the time. So it goes back to before RFCs. It's been constantly worked on and improved as we go forward. Let's have a look at some of the fields there. So clearly we've got the source port and the destination port. Now we've got 16 bits for each field, which means that the maximum value in there is 65,535. What we're commonly going to see is the source port. If we're connecting to a well-known port, this is going to be one of the ephemeral number, whereas that destination would be the well-known port of that server or service that we're using. Obviously, exceptions to all these rules. Or if it's coming the other way, it's going to be flipped around. Now we know TCP is a reliable protocol, and the reason why it's a reliable protocol is because we can get retransmissions, we can get acknowledgements, we can make sure that it's got across there. And the way that works is with sequence numbers and acknowledgements. So these sequence numbers, obviously we've got 32 bits, so from up to 4.2 billion, so quite a few there. But it's not impossible to wrap around. So we need to have a mechanism in place for that, and we'll discuss that in a bit. So that's our sequence and acknowledgement numbers. We've got the header length. Now, the standard TCP header length we're going to see is 20 bytes. However, in the synchronization messages, we're going to see that can be a lot bigger, because that's where we're going to be negotiating, well, not necessarily negotiating, but we're going to be just, between both endpoints saying, this is what I support. These are the options that I can do. These are the ones that I can't do. And we'll look at those in a bit. Okay, we've got a few bits that are reserved. And again, these used to be a bit bigger, but we're adding new features all the time. We've got a number of flags. We've got this nonce, we've got the congestion window reduce, and the explicit congestion notification, or encountered, should I say. And again, if both devices support that feature, when congestion is experienced, this is a way that the IP layer can actually talk to the TCP layer and say, okay, you need to inform the sender that there was congestion experienced, and then we can let that sender know that there's congestion on the route. Otherwise, they wouldn't know. We've got the urgent flag, which is used in conjunction with the urgent pointer. So if there's some information that's contained that needs to be actioned straight away, that would tell us where it is. We've got the acknowledgement, and we'll see that that's used quite a bit. We've got the push flag, end of letter. This is a flag that when it's set, both sides of the communication, it's basically telling them that this needs to be actioned straight away. So for example, if you're using SSH or, to configure a device, when you press a button on your keyboard, you want to see that button on your terminal screen, and that push flag would be set to make sure that that's coming all the time. We're not waiting for those buffers to fill up before we send information, for example. We've got the reset flag, and that is can be used for fingerprinting. It can be used, which not always a bad thing, but can be. So if we try and connect to a port that's not expecting communication on it, it's going to send us a reset flag. And that is a way that we can, port scanning is done basically. We've got the synchronization flag, and again, this is the one that's going to be set during the initial handshake. We'll discuss that a little bit later on. And then we've got the fin when we want to close that, connection down. The next field we've got is the window size. Now the window size is also 16 bits. Now that only equates obviously to 65,535, the same, representing bytes. Now if we work that out, that's only a 64 kilobyte window. When we're talking about windows as well, what we're really saying is this is my receive buffer. This is how much information I can have before it's been acknowledged. Okay, so this is a way that we get flow control. Obviously, that's not a great size. So we'll look at how that's been improved as we go and look at the options. We've got a checksum value, a header checksum, and again, same as the IP header. This is generally going to be offloaded to the NIC card these days. Okay, so Wireshark on the sender side anyway is not going to see a value here, and that'll be disabled by default as well. I mentioned the agent pointer. Some of the options that we have then, so we've got the maximum segment size. Okay, so that is us telling the other side, this is the maximum segment size that I support. Okay, they don't negotiate this value. Okay, it's whatever is the lowest, that will be the one that is decided. Okay, it's not a negotiation. The point to note on the maximum segment size is that we're not talking about the TCP header and the data that's contained in there, in that segment. We're talking just the segment. We're not including the TCP header. Okay, I mentioned the Windows size being relatively small for modern networking. So with the Windows scale feature, we can scale that up basically to the power of 2. So if, for example, that Windows scale size was set at, say, 7, then we would times whatever the window size is advertised as, we'd times that by 7 to give us our actual buffer size. We've got selective acknowledgements. Now, again, previously the way that TCP worked or does work now, because SAC is not enabled on every single device, should be, in my opinion. But if we could have received packets of data, but if we've lost one, we've got to acknowledge to get that one that we've missed. And say we could have received an additional, 20 bytes, 200 bytes, absolutely fine. But because I've got that I haven't got selective acknowledgements, I'm having to go back, and then the sender's having to resend all of that information again. So with selective acknowledgements, what I can do is I can set a left edge and a right edge and say, look, I've got all of this, but I didn't get that. Send that to me, please. Okay, timestamps that can be used for multiple things. One of the things that I mentioned about wraparound, so this can give us what's called pause, so it can give us a protection against wraparounds. So it understands that instead of it's not seeing the same sequence number again, it's a different sequence number, and that timestamps is what makes it different. And then we've got the no operation field, and this can be used as padding because basically the TCP headers have got to finish on a 4-byte boundary, and we've got to get the options to start on a 32-bit boundary as well. And I mentioned that data, the data field within that segment. Remember that this is what the maximum segment size actually is. So let's have a look at that in Wireshark. So let's get some TCP up. Stop that capture. We've got enough in there. I'm going to restart that in a bit. Okay, so what I can do is just collapse all of these. Okay, so if we have a look at the transmission protocol, control protocol itself, so we can see here we've got the high level view of it, basically telling us the source port, destination port, what the sequence number is, and the acknowledgement and the length itself. Source port, destination port. Now, Wireshark's added this information in for us. This is not actually within the header, but we've got a stream index. So what we're able to do again in Wireshark is we could add a column, for example, and say, okay, this is all of the different stream indexes that we've got for TCP. When it comes to the sequence numbers, we can see what Wireshark does automatically. And again, we can turn this off, but it's going to give us a relative sequence number. So instead of what you can see what the actual one is here, which is what, 2 billion something, it's going to give us a relative number. So it's easier for us to understand. But there could be times where we don't want to make it easy. I don't know. So we could turn that off, but we can get that information anyway. Okay, we've got our header length in here. We can see some of the flags that have been put in for this one. Yeah, and then obviously our payload there. So let's have a look. So if we want to set some information, so let's have a look at the flags here. So what I want to do is I want to find all of the SYN flags that have been set. So what I can do is I can use this field, even though this SYN flag's not been set yet, I can right click on it and I can say I'm going to prepare that as a filter, and I want to prepare what's been selected here. But instead of it being off, I can turn it on. And I need to really clear this out because it's struggling a little bit. Okay, so that has isolated all of the packets that contain the SYN flag on, that are there. So what I want you to see here, I'm just going to drag this across a little bit and move myself out of the way. So we can see all of these options that have been negotiated, okay? And it's going to tell us these in the sort of high level information of Wireshark, but we can also look into them in a bit more depth as well. So if I click here and go to the options, we can see that these the maximum segment size has been set. We've got a window scale in there, so that's good. And we've also got SAC being permitted. Now, what we're not seeing here is we're not seeing timestamps, which would be useful as well. But that's some of the options that we've got within within TCP. Now, what's important to note with the maximum segment size, and we'll look at this a little bit later on, is that, remember, it's not a negotiated value. Okay, so if there's a misconfiguration somewhere, it's quite possible that the client thinks something different and might send a smaller rate, and likewise the server. If there's something in the path of the packets that has modified that field for whatever reason, some network tuning or whatever, and it's not being done in both directions, then that could cause us some problems. So if I wanted to maybe have a look at all the different maximum MSSs that have been set, I can just right click on that and I can apply it actually as a column. In fact, I don't want to use that one. Ooh. Freeze a little bit here. Okay, I think we might need a little restart here on Wireshark because we're frozen up. Because this capture's a bit big. We're moving a little bit now. So let me turn this one off. We'll give this one more go. Okay, there we go. I'm just going to turn off the colouring filter because it's a little bit angry. So we can see there, we've got the maximum segment size value in each of these fields. So we could obviously we can sort on that, and we can have a look at what's the biggest, what's the smallest. So the general size that we're going to see is going to be 1460. So we know that the MTU generally for an Ethernet packet is 1500 bytes, obviously unless we're using jumbo frames, which we don't really use so much now, minus the IP header, minus the TCP header. Okay, so really 1460 is a usual value that we're going to see in there. So just another way we can create a column, and we're going to do a little bit more of that a little bit later on. So Holly, I think that might be a good time for any questions so far.
Only so far. So if you've got a question, if you want to use the Q&A function down at the bottom of this webinar, just drop it in there and I can get Brian to answer it for you. Not get anything just yet.
So hopefully that's a good thing that there's not any questions so far. But if have we got some stuff coming in, have we?
So
good one, Jack. I like that.
What is a packet?
It's got a big sign on it saying walkers, and I'm going to be having a bag after this. Okay, so if there's no questions, what I'm going to do now is I'm just going to move away from Wireshark for a little bit, and we're going to talk about a little bit of plumbing.
I've just got a question come through.
Come on then.
Right, so regarding permalink on an Ethernet frame, can we see that on Wireshark?
Zarina, you have to explain permeable. I'm not sure.
Was it programmable? Sorry, it's mine.
Oh, the preamble. Sorry, that's fine. So the preamble, no, I don't think so, because that's it's kind of got rid of on the NIC itself. So no, that wouldn't be seen in Wireshark. But it's important to know that it is actual bytes that's on the network. But it's a really good question. No problem at all. Okay, so what I want to go over is just some of the different ways. And those familiar with Happy Gilmore, which hopefully is all of you. If you're not all familiar with Happy Gilmore, immediately following this webinar, go and watch it. It's a fantastic film. Okay, so it's not just a case, unfortunately, of just tapping it in. We've got to bear in mind, you know, production networks and you know, time, and really all of this, you know, how to actually view the traffic should be something that's planned into part of the network design. We've got monitoring devices, you know, that SNMP, you know, NetFlow, all of these stuff, it needs to see copies of the traffic. So we should have some stuff there, but it can be difficult for us to actually get a good trace and to find out what's going on when we don't have these things available. So let's just have a look at some of the options that we've got. So one of them is here, and I'll explain the diagram a little bit. Okay, so this is a non-aggregating tap. Okay, so tap being like traffic access point, may see referred to as terminal access point. But what we're doing here, so the purple box is, hopefully you've realized, is the actual tap device itself. And what we've got here is we've got the router connected. We could think of this as one cable and one into the switch itself. The reason why I've used two different colors here is just to highlight the fact that we've got traffic going in both directions. Obviously, it's a full duplex link. So if, for example, these are a 1 gigabit link, it could be sending 1 gigabit in one direction, 1 gigabit in the other direction. So if we was to put this onto a single port, it could possibly, depends on the device, of course, but it could possibly overload the port. So non-aggregating taps is a way that we could spread that out. But what we would need on the capture device is we would need two separate interfaces, and then we'd need to merge those together. Okay, so just be aware of that one, so a non-aggregating tap. So with most non-aggregating taps, it should fail open. So if the power is lost, it should just allow the connection to be, to carry on without causing you any issues at all. Okay, and the next one we've got is an aggregating tap, and that is going to put both of the directions of traffic into one monitor port and allow that to go to another device. So if, in this example here, we've just got a DPI device and an analyzer, so Wireshark. Points to note on that is the same thing applies. Obviously, we just need to be careful that we don't overload that port, because if it does, depending on the device itself, is what behavior you're going to see. So it could be fine. You might not have a lot of traffic going through there, and you might not get overloaded. But if it is, it may just stop working altogether, or it may just start dropping lots of packets. And obviously, if we're trying to analyze a problem and we don't see the packets that we need, again, obviously that's going to cause us a massive problem. Okay, so we've got a different type of tap here. So this is a span tap. So if we look at this, what we've done is we've set up a port on this router where we're mirroring the traffic that's being received here. So both directions on this link, and it's going through, connected into port A here. Now, what we don't want to do is we wouldn't want to have 4 separate span ports set up on a router. Even if we could, it'd be a lot of resources being used. So this is a way that we can get a tap off a certain device, and then we can export that to multiple different devices without overburdening this one single device, saying, oh, we need 4 span ports on there to go to 4 different things. Again, points to note though on these network devices, they're a network device. Their primary job is to route traffic, in this case the router. So if it was being overloaded with traffic, the spanning feature would probably be the first thing that stopped working. So if that's something, this monitoring that's taking place, if this is something that needed to happen, 100%, which really, we wouldn't be doing it otherwise, would we? We need to watch that. So one of the better options, maybe, depending on what you're doing, is using a filtering tap. So instead of seeing every single packet, we may filter it within the tap before it gets exported to a network monitoring device. So I kind of alluded to it earlier. So if it was maybe VoIP or some other protocol that we business critical application, basically, we could filter that within the tap, so we just get those packets that we need set into that device. So if it's something that you're monitoring within the NOC, you could be looking for a specific pattern, or analysis to do a specific analysis of traffic. We could set that filtering up in order to do that. And really, one of the the sort of the easiest, most common ways, not necessarily easiest, but the easiest way is just to set up a simple span import on a switch itself. And again, because if I just connected into a switch switches, doesn't it? So if I just plugged my analyzer into a switch, and the security wasn't very good, so I'm just walked in there and done it, and forget all of that. But let's say the port was on and I connected to it, there was no problems at all. All I would see would be broadcasts and multicast. I wouldn't necessarily see the conversation that's ongoing. So I would need to actually mirror or span that port in order to see a copy of it. Yeah, that's pretty much the bit on taps that I wanted to cover. So is there any questions at all on some of the different taps that are available, where we're going to put those in, some of the considerations that we might need to consider? I should mention one other thing actually. A lot of people will say, "Oh, we could just use a hub," and you can. That's obviously there's complications that could be brought in with that, but it is quite difficult to get a hub that is actually a hub these days. So if you go onto Amazon or something and type in hub, and you'll probably see, get some little two port, it'll be called a hub. It'll actually do switching, so it will still give you the same limitations that you had before. So just bear that one in mind. Okay, any questions on that at all?
So we have one from Bilal. Can we use Wireshark on remote devices like ASAs and routers? If yes, then please explain.
Yes, we can, and it just depends on what method that you want to use. So, for example, we could say that we've got a router here. We can, depending on and obviously different vendors, etc. But we can set up a span on that router where we could analyze that traffic directly, or we could do it in this sort of a way. So maybe not with a non-aggregating tap, but with something like this. So this would be, whether it's a router or firewall, as you mentioned with the ASA, it doesn't really matter. We can still see the traffic that's going through. And obviously because of the type of device that the ASA is, it can do different, modifications where it's needed on those packets. Or if we've got, load balancers or anything else at all, yes, we can capture that traffic on Wireshark. Does that explain it, or do you need a little bit more information? Sorry, I'm not seeing. Bilal, does that answer your question?
You just want to, yeah, no, it does. Yeah.
Excellent. Okay. Okay, so what I'm going to do now then is we're going to go back to Wireshark. And we're going to have a little play around. So first off, I'm going to okay, so at the moment, so what I want to go through really and just take a little bit of time on is looking at how we're really going to set up Wireshark so that it's useful to us. So if we think back to that, I think it's I don't know if it's Matrix 1 or Matrix 2, where the green code's coming down the screen and really it doesn't make any sense. We want to try and sort this in such a way where we can make things clear to us. So one of the first things that's really useful. So I'm on this frame here. Let me just collapse this. And before I go on, I'm just going to disable, where's my preferences? There we go. And so I just want to turn that off because it's annoying. Okay, so one of the first things that we really want to do is we want to be able to find out whether something's, slow or not. Now, really, the most important column for this is the time. So if we have a look at the time, we can see here that by default, it's set to the second since the beginning of capture. And this is fine. There's no problem with that at all. We can leave that one on, but we can change it, and we can change it to a number of different things. So be aware of that one. Now, there is obviously, between each of these packets, you can see that the time's incrementing. Clearly, this is the time since the start of the capture. But it's not really easy for me to see the actual time between these packets. So what I want to do is I want to add a column to make that a little bit clearer to me. So if I just click on any of these columns and I go into the frame itself, we can see here, hopefully you can see here, that we've got the time from the previously displayed, from the previously captured frame, the time delta, should I say, and we've got the time delta since the previously displayed frame. So what I can do is I can right click on that one and I can apply it as a column. Now, obviously with the columns, I can move them around and it makes sense that I'm going to want it next to this one. Okay. So I can see the actual difference. So the time it's taken and between those ones, and it's going to allow me to calculate some things actually what we're going to look onto. But at the moment, as you can see, that looks a bit rubbish, doesn't it? So we want to change this and make it a little bit better. So if I right click on that and edit the column, I can change the actual title of it. Okay, the field that it's working with is, we don't need to touch, we just leave that one the same. But if I just turn this one down to time delta and click OK, and there we go. So now it's a little bit clearer to me. Now it might not be. If you might want a little bit more space in there, and the same as sort of Excel, we can drag things around, we can align things centrally, we can align things to the left. Whatever works for you. Bear in mind, if you're in a role where you're working as an analyst all of the time, this is going to be where you're going to spend a lot of that time. So you want to make it so it's easy to read, it's comfortable for you. Okay, so that's one of the things that we can do there. That's just a simple thing, adding that time delta to it. So one of the things when we're doing an analysis of TCP in particular, we want to be looking at that three-way handshake. So let me go back to here. And again, apologies for those that are maybe like, three-way handshake, a bit basic, but it is important stuff. So if let's have a look at the site, do a three-way handshake. So we have a device on this side, excuse my amazing artistic ability. Okay, device on this side, and we want to set up a connection. Okay, so as I've mentioned, the first thing we're going to do is we need to send across a SYN. Okay, and that SYN message is what's going to contain details about my options. It's going to give me the actual sequence number that I'm going to use. Remember that both sides are going to have a different synchronization number that they use. Hopefully, within that SYN message as well, it will say I support selective acknowledgements. Here's the timestamp information. Here's my window scaling, for example. We come back, with our SYNAC. I'm acknowledging your synchronization message. Here's my own. And then we acknowledge that. And that is the three-way handshake itself. And the next packet that goes out across to here, maybe, I don't know, GET request, for example. So that's the three-way handshake. Now, the reason why I mention it, and I will go back again to Wireshark, is because this is really can be a big revealer for any problems that you find on the network or problems that you've encountered. So things like the maximum segment size, things like the window size, things like SAC being enabled, and this is only information that you're going to see within the three-way handshake. So if I just show you this here, again, we just collapse this. If I go to my flags again, and I'm going to say, okay, SYN, but I don't want the SYN included. Okay, so I've got no SYN information here. Okay, so when I have a look, okay, we can see the time. We can see the timestamp. What we can't see is any other information that was negotiated. So we don't know what the maximum segment size was negotiated, for example. So if you are doing this for real and you're getting customers sending you packet captures, do stress to them, try and when they're trying to capture the problem, that really you want to see that three-way handshake taking place. Okay, so what I'm going to do now, I'm just going to open up if this comes up. We'll do a little bit of a comparison. Okay, I want to get rid of this one for the time being. That a little bit smaller. Okay, so we've got our client side of this capture, and we've got the server side. So what I want you to look at, or what I want you to see and understand, is you need both sides of the story when it comes to the packet captures. Now, clearly, it makes sense that if we're doing if we've got an issue on a client, yeah, it's a good place to start. If we can get a capture from the client itself, if that's possible. But really, we need both sides to tell the full story. So we can see here that the source here 10. This is on the client side. Sent this synchronization message and included in there his maximum segment size of 1460. And we can see, if I go into the options, we can see that there. So he's saying my maximum segment size is 1460. We can see the SYNAC coming back, and the servers actually responded and said, okay, this is only 1380. So this is what they will use for that negotiation. So if I have a look at the server side, just remember that value there that was sent 1460. The servers received the SYN message, but what's that number here? So that number is only 1380. Now, the servers responded with 1460. If we have a look at the client side,
what is it? It's also 1380. So what, again, is important to understand is that devices on the path of the packets are able to change that maximum segment size value. And they may need to. There may be something, you know, some tuning on the network where they want to turn that down to a certain amount. But that's something to, you know, to understand. Okay, what else we can do with the having the time delta set is we can have a look at the sort of initial round trip time that's taking place. So I can send my synchronization message. The next message that I'm going to get back is that SYNAC, and I can see there that the round trip time is about 10 milliseconds. Now, is that normal? I don't know. It looks perfectly normal to me. But that is where it gives you a kind of an initial baseline for you to work from. Without that, you're blind. You don't know. You know, if someone's just sent you this, you need something to base things on. So, and that is, you know, one thing that we can do initially, just get that initial time worked out. If we have a look at it from the other side, okay, we can see that the SYNAC has been sent. So this time, really, just to remember, obviously the client sending the SYN receives the SYNAC back. The first message that the server's actually sending is that SYNAC. So we'd be calculating the round trip time based on the ACK that comes back. And we can see that there, and again, you know, is about 10 milliseconds. So there's, again, not anything too untoward there. Okay, any questions on the three-way handshake, the options that are contained within it, or anything else at the moment?
We have two currently. Mo asks, will you show any CLI examples using T-Shark?
We're not going to be covering any T-Shark today, unfortunately, no. But if you please, you know, speak to Holly and, you know, put it on the feedback. That's something that you'd like to do in the future, and I'm sure that can be done at maybe a future webinar.
Perfect, thank you. And Zarina asks, regarding the time column on Wireshark, would you be able to make it more humanly readable format, such as hour, minute, second? For example, the second line in the time column, 01003374, doesn't really make sense.
Right, okay, so let me just break that down a little bit. So it maybe doesn't seem like it makes a lot of sense at the moment, but it is really crucial that we can, obviously, if we're working in minutes and hours, is just not really something that we can do in it's just not a time that we can work in. You know, we work in, you know, milliseconds, we work in microseconds. That is what we work with. But so just to make it a little bit clearer, maybe explain the time a little bit. So obviously this is in seconds. So 0, if that does spill over, and let's have a look at this trace file, so we can see this packet here. So the packet 29,953 arrived 14.39 seconds after the start of the capture. So we can see how fast all of these packets are being sent. So really using anything more than milliseconds and microseconds is not, we're not really going to be able to see the issues that are there. It's going to be really difficult for us to troubleshoot. But so just to understand that, so obviously we've got the seconds column, everything left-hand side of the decimal point. The next 3 fields is going to be milliseconds, and then the next 3 fields after that is when we're talking about microseconds. Okay, so hopefully that explains it a little bit better. But yeah, really we want to be working with those formats. Does that answer your question? Sorry.
Yes, it does.
Okay, excellent. Okay, so if there's no other questions on that at the moment, let's go back up. Let's have a look back at the client side. Okay, so we've seen that the three-way handshake has been completed. We've seen that the options that are contained within it, and we can see that the client has made a request to the server for a HTTP document. That's been acknowledged, and then that data is starting to be sent. Okay, so let me just stick the coloring rules on. Okay, so we can see here now, so this is where the coloring rules are useful. So I just want to, again, just show you one other little bit here that can be useful. And that is this intelligent scroll bar here. So when we've got the coloring rules on, so obviously we don't have it now, when we turn the coloring rules on, we can see the definite changes in the color, and something that we can click to, and well, it didn't get very well there, did it? But when we click on that, then we should really get to potentially any problems that we're seeing. Okay, so what we can see here is that we're being told that the previous segment wasn't captured, so something's being lost. That could be down to the capture method that's being used. It could be down just a problem on the network. We've also got a duplicate acknowledgement here, 19 and 1, and we can see it's actually been sent again here. Let's just take a little bit more of a look at that. So we can see here, and this is what is useful. So we can see the SAC being used. So we can see, instead of me saying, okay, I need you to resend all of the packets after this acknowledgement, I'm saying I've got all of these. This is my left-hand edge, this is my right-hand edge. Okay, it's the others that I need. So let's just have a look at that in the details pane as well, so you can see that one. So just collapse this. So there we are. We can see within that option field there, we've got that selective acknowledgement, and it's telling us, so this is the left-hand edge, this 10.945, and this is the right-hand edge, 13.681. So we're saying everything here I've already got, but this is what I need. This is what I'm expecting next. Okay, I need this packet. Okay, let's have a look at that on the server side. So I'll put the coloring rules back on. So let me write down at the bottom here, aren't we? Okay, so we can see where we've got. Okay, so we've got a different duplicate transmission there. And not the number and the ID here. So what we could see, if we're getting an acknowledgement that's not happening, this could go on forever. So this could be 32 and then maybe say 190, for example. So it could just keep ticking on and on. So it is something to look at there. So let's have a look. We can use, if this is in my way at the moment.
Sorry, Brian, just to interrupt. We can only see the client side. We can't see the server side.
Oh, right. Okay. Sorry. That's because I've got a different window, isn't it? Not bad.
Yeah, there we go.
Hopefully you can see that now. Sorry, guys. Right. So I'm just trying to, at the moment, get rid of. Okay. Hopefully you all still hear me. I've just turned something off. Okay, so just another little tip there so just be aware of this expert information button that's down in the corner as well. And this can be really useful for just giving you a high level of information and potentially warnings or notes about the conversation itself, about that trace file. Another thing that we can do is we can have a look at the conversation. So if you're initially receiving this trace file, you might not get a lot of information from the customer themselves. They may not really know, client serve or whatever. They will just be telling you, okay, we've captured this data, we've seen this problem. Here's 2 gigabytes worth of trace files. Fill your boots, kind of thing. So one of the things that we can do is we can have a look at the conversations field, and we can see here, obviously, in this example, we've got this conversation that's going either way. But with a bigger capture file, we'd have more conversations taking place. So that's just something to bear in mind as well, that we can use. Okay. Oh, sorry, I wasn't going to do that. Okay, so I want to show you how to quickly sort of find these errors, or another way that we can do it. So we can see here we've got a duplicate acknowledgement. So if I wanted to find anything like this, I can apply this as a filter, and now I can see all of that information here, okay, being highlighted on the screen. So we can see here, as I was mentioning before, we can see all of these duplicate acknowledgements, and we're missing this packet here. We're missing this byte, should I say? Okay, and we can see these are just going to keep going and going and going and going all the way down until eventually that connection is going to be terminated. Right. So another thing to sort of understand and be aware of, we can see those issues that are there. Now, obviously, if we was only able to see one side of the traffic, we're not going to see the full picture. So it is important that we can try, or at least request from the customer that they can get us a capture file that's going to be from the server side and the client side. Okay. So has anyone got any questions on any of that? So just a reminder, some of the key things when we begin to analyze a trace file, we mentioned about the time. It's really important to set a delta on there. It's one of the key fields that's recommended to be added, so that we can see delays as they come about. Now, a 20 millisecond delay, it doesn't seem like a lot. It's not, I can't go, stop a clock and say, oh, that was 20 milliseconds, that's just gone by. But all of these 20 milliseconds add up. And then if it's 40 milliseconds, 80 milliseconds, suddenly, we're cranking up towards a second. And these kind of delays, when they're multiplied across the network, hundreds of thousands of times, that's when we're going to get severe problems on the network. Okay. Any questions? Sorry.
One come through from Ian. Is there anything in here that could differentiate between network and application delay? It's a very good question. I'm not within this trace itself. I think, to be honest, one of the big things, and this sounds like a little bit of a finger pointing exercise, but it goes back to what I mentioned at the start when we looked at the OSI model. Now, we can get a capture file, and we can get it from the client side, and we can get it from the server side, and
and we can say, okay, something is happening here. Let's go down this path as the next path of investigation. So things where, and it's obviously not within this this trace, but things that would really point towards it being the application side would be things like a slow clearing window. So where we would see that the source, the receiver is constantly advertising a really small window, and then he's clearing a little bit, server sending that new information out to it, but then he's having to wait again to clear it. And that's probably down to the, I'm not an application specialist by any stretch of the imagination, but that's probably down to the way the code's been written, and it's not going in there and clearing out those buffers fast enough. And as I said, we the way modern networks are, the speeds that we've got, we're putting a lot of a burden on them to get those buffers clear. And particularly if we're not using things like, window scaling, that's where we're going to see, more problems, because we've got a tiny receive buffer. And without that bigger buffer where, we can increase that receive buffer size to, a gigabyte, for example, that's where we're going to see those issues. So really, what Wireshark does is any packet analysis software does is it allows us to kind of get in the parish. It's not necessarily going to be able to say that is exactly what your problem is, but it gives us a direction, a path to go down next. We can do, we can look at something where we, as I mentioned about the Windows receive buffer, I can say with some certainty that if we're seeing that, it is probably the application that's causing the problem. But, we don't like to say 100%, do we? We'd like to say, well, it depends on these factors. So within this trace, no, but yes, we can get an idea through Wireshark. Okay, so hopefully you can see that. Okay, so so that's a little bit about setting up a particular profile. We can make changes to it. So if I find a particular problem, I can add those display filters, filter on it, and lead to the point where I can make a judgment and say, yeah, that's this is your issue, or this could be contributing to your problem. It could well be, and this is something that just has to be accepted, I guess, is that we may not see the exact problem. It may be a combination of problems. It may be that we're not using window size. Maybe we've not set that maximum segment size within the options, and we've defaulted to a really small segment size to use. Now, is that going to stop the network from working? No, but it's not good, is it? It's a problem. It's another thing that could possibly cause us problems. So that is something that we need to appreciate. We say it's not an exact science, but the packets don't lie. Okay, so we can see, we can say, well, that is a matter of fact, we've got a delay of 40 seconds before this retransmission was started. We can't argue with that fact in a trace file. So when it comes to the next step of the investigation, what's causing the problem, then we've got that evidence, we've got those packets ready to support us. They're not going to lie to us. They are what they are. Okay. Is there anything else anyone wants to look at or go through? I'm just going to start a sort of general capture, see if we get some different stuff coming in. Is there any other questions? Anything that anyone else wants to go through at all? Well, Holly, that's really what I wanted to cover for the presentation, really. Obviously, if there's any questions from the audience at all.
Yeah, we have one just come in. So from Jordan, if the device I'm running a capture on drops a packet, will we see that, and how could you differentiate between receiving an RST packet from the remote host and one generated locally?
So you would be able to distinguish one from a remote host because the source would be the remote host, the source of that reset. So that would be the simple one for that one. When it comes to lost packets, Wireshark will be able to see that there's packets being lost, provided that there's been further packets sent afterwards. So if, for example, we've sent segments 1 to 10, but 8's been lost, well, Wireshark knows that 8 existed because it received 9 and 10. So it would be able to tell us that there's been a lost packet there. So to answer your question, yes, Wireshark would understand that there's a packet being lost somewhere. And so to be, with the two devices that are in that communication. Okay, so I've really not got anything that we can go through in too much more detail at the moment. All I will say is to just summarize briefly what we've covered. Wireshark on its own is a fantastic tool, but we do need that understanding of the different protocols that we're using, the different behaviors that work in order for us to really be able to analyze what's going on in a granular manner. We need to understand that capturing the packets from one side, it may be enough, but really to get a full picture of what's going on the network, we want to be capturing from multiple places and maybe using something to merge those files together. Or and another thing to remember is the packet ID as well, which is really useful for mapping those packets together as well as the sequence numbers, particularly when there's duplications that's been made on there. We can't always say for certain. Obviously, like I say, the packets don't lie. That is what was seen, and that's what it was seen as at the time. That was what the behavior was. But if you you think you've got a slow server, for example, then it may well be doing something on the other side. It might be a server behind that's trying to get your server you're connecting to is trying to get information from, that's running slowly, rather than the actual server you're connected to. So remember that there's a bigger picture, and Wireshark is going to hopefully lead you to the path to find the next point in your investigation. But it's not always the end of the investigation. It's the start, I would say. Just to finish off, Wireshark.org. Obviously, that's the place to go for downloading a new copy of Wireshark, or to get the latest version, update, whatever. There's lots of information there. So information on the ask.wireshark.org. So questions that you have, people go on there, can answer those questions. Packetbomb.com, Carrie Rogers' website. Again, these are people that have been capturing packets, doing this for a long time. Really good information that's held there. The Chapel University, so Laura Chapel, who's wrote the Wireshark books. Again, really good sources of information that you can go out there and get. And again, just a couple of thanks for people that have helped me on putting the presentation together. Sezgin Bayrak, Chris Gurria, Kerry Rogers. That's really that one. So yeah, we do have their courses running all the time. So there's the 3-day Wireshark course that runs, which is basically the Wireshark 101 course, and we have the 5-day course, which is fully geared towards the exam. And that's it. Yeah, sorry, that's all I have for you. Thanks, guys.
Lovely. Thank you very much all for attending. And yes, just to let you know, this is being recorded and we will share it around with all of you after this is all done.
Okay, great stuff. Okay, so I'm going to stay on the chat for a little bit. So if there's any questions, please go for it. So Chris's question: are taps just mirroring the traffic to a different port? They're mirroring what's actually being received on a particular interface, and yes, to another port for us to connect into. So for example, if I just had a bog standard switch, didn't have any taps in the network, I could configure that switch to send a copy of a particular interface's traffic to send to my interface. So that would be an example there. That's a really good question, Paraf. I would say both is my honest answer. Really, you want to, depending on what configuration you've got on that firewall, we want to be able to really understand what's being done. We want to see what the packets were like before they have had any policies applied on them, and what they're like afterwards. And we made the example about the maximum segment size, and we showed that the client and the server both offered different values to what was actually agreed on, because of a device that was configured to say this is the actual value. Okay, so that works exactly the same way as a firewall. So if we do have, or when, before that firewall even goes in, really as part of testing, yeah, I would definitely recommend capturing on both sides of that before and after those policies have been applied, and that's the only real way you're going to make sure that, number one, there isn't any configuration that you've done that's potentially going to cause a problem. But it's not always just down to the engineer. It could be a bug. It could be something that's not quite right with that device, and it needs updating, it needs patching. Maybe it's a project that's been ongoing for 6 months, and there's 2 or 3 vulnerabilities that have come in at that time. So the only way to see that properly, but would definitely to be both before and after. So hopefully that answers your question.
Right, thanks everyone, most appreciated, and hopefully we'll see you soon at the next one.
Yeah, have a great time everyone. Stay safe. Bye-bye.
Bye.